Okay, let's restart. We have obtained the expansions of P and P prime in this way. What is good with these expansions? Well, by computing the square of P prime and the cubic polynomial of this P, we have such expressions. So summing up these shows these singular parts cancel out. And this part is holomorphic. So what? Recall that P prime is an elliptic function. And the elliptic functions form a field, namely a polynomial of elliptic functions is again an elliptic function. So this is an elliptic function. And this is holomorphic. Well, since we are considering Taylor expansion at 0, so a priori this guarantees homomorphicity at 0, but actually because of double periodicity and that this has poses only at the lattice point. This is homomorphic on the entire plane, which means that such a combination is an elliptic function which doesn't have a pole. Namely, it is a constant. Well, what is the constant? Well, this part vanishes at 0, so the constant is equal to minus G3. Namely, we obtained such an equation. What is this? Well, in other expression, this means this, or roughly speaking, it gives such an expression. If we integrate this expression from infinity to P of U, which corresponds to zero to U. So at 0, P function takes value infinity. So we integrate in this way, and we have, well, roughly speaking, this relation. Therefore, U is expressed as an elliptic integral from infinity to pu, which means that pu is an inverse function of this elliptic integral, which was the definition of p last time. So this construction by the series is consistent with the previous definition. Actually, we can construct the inverse function of the Abel-Jacobi map by using p function and its derivative. Recall that when we considered the inverse function of elliptic integral, we considered in this way. This is some projection. We have some. Well, actually, this is not C2, but anyway. Yeah, we have some pair of complex numbers. We project it to C. And this is Abel-Jacobi map, and this was the inverse map. And this is usual mounting out by the lattice point. This was the p function last time. And well, so elliptic integral, the p function as the inverse function of the elliptic integral. And so this is the inverse mapping. And so this inverse mapping is essentially Abel-Jacobi. And that is constructed by this p function as follows. Well, the bijectivity or this is an inverse function of this map can be proved as follows. Yeah, which is an exercise problem. And first, this pu has a pole, so this is not holomorphic as a usual function on the complex plane, but we are mapping to the compactification of the Riemann surface. So actually it is holomorphic even at the pole, because pole corresponds to the infinity at of the elliptic curve. We have to check that this what is the coordinate at infinity. And at such 3 points in between the edges of the parallelogram and the center of the parallelogram, or p prime has 0. And well, this and also evenness, oddness, or prove the bijectivity of this method. Well, please try. And more important or more convenient property of the Weierstrass function is that it is a building block of the of any elliptic function. Or you can find some rational functions which express an elliptic function in terms of p and p prime. Well, how to find these rational functions is a little bit complicated, so I put several hints in the exercise program. We do not use this property further, but it shows that p function is a fundamental object in the theory of elliptic functions. Okay, next, well, let's discuss the addition of the function, which is one of the quite important property of elliptic functions. Well, so recall that elliptic is isomorphic to C over gamma, which has a group structure in this way. Namely, since gamma itself has an additive group structure, additive subgroup of the group of complex numbers. So this factor has also a group structure. And from which actually follows the addition formula of the P function. Well, and there are many expressions for the addition formula of P function, but probably the most, the simplest way of writing it is by this. So, expression by a determinant. Here, three complex numbers are related by this relation, or it is sufficient that the sum is sum belongs to the lattice gamma. Then this determinant vanishes. This gives a relation between P of U1, P of U2, and P of U3, which is equal to P of U1 plus U2, or and also P prime U1, P prime U2, and this quantity. So we call that examples. The addition formula for sine has such an expression. Well, maybe you don't like this form because it has two functions, p and p prime of u1 plus u2. But later, we can rewrite that formula by in this way to express p of u1 plus u2 in terms of p of u1, p of u2, and p prime of u1, p prime of u2. So for the moment, let's prove this expression. Well, since if P1 and PU2 are the same, then it causes some problem. So for the moment, let's assume that they are different. But it is not a very serious limitation because we can continue the formula analytically afterwards. And well, let's take solution of such linear equation for two complex numbers a and b. If u1 and u2 are fixed, then we have some solution. Well, this is an explicit formula which we do not use now, but if you would solve the exercise, then it will be necessary. Anyway, let's take a and b, which satisfy this equation. And compose such a function, such an elliptic function. Well, this is of order 3 because p constant is just a constant. P has a pole at the origin or at lattice points. P prime also has poles at lattice points. And the dominant pole is the pole of P prime. It is of order 3. So it is an elliptic function of third order. So what can be said from this? Well, we proved that such an equation has solutions in the period parallelogram. And the number of solutions is the order of that elliptic function. And in this case, we have 3 solutions. Well, by definition and this relation, U1 and U2 satisfy this relation. So there should be another solution. So let's call it user. Then we'll have proved that sum of such solutions is equal to sum of poles of that elliptic function. But there are only one pole, which is 1/3. So the sum is 0. Of course, not about. Which means that this solution U0 is equivalent to U3 modulo gamma. And since FU0 is 0 by definition, and FU3 is equal to FU0 by the periodicity, we have such an equation. Namely, we have found 3 zeros. In other words, we have such an equation. We call that f of u is this is it. This is the components of this left-hand side. Okay, so what? This vector is not 0, as you see, because there is a non-zero component here. What does this mean? This matrix should be degenerate. Because this linear equation has a non-zero solution. This means this equation. That is the proof of this addition form. And actually, yeah, this addition formula includes not only P of U1 plus U2, but P prime of U1 plus U2. But actually, we can eliminate this P prime because we have such a differential equation. We have such a expression for P prime. Of course, for U1, U2, and U3. So by substituting this expression here, we have some cubic equation for P cube. And well, cube and over if such a cubic equation has a set of solutions, alpha, beta, gamma, then we know that this coefficient is sum, right? This is this is well, this is just a result of expansion. So what? So please check what is here. And you will see this relation. And just move these two terms to the left. So these are fundamental properties of the Weierstrass function. And actually, thanks to this addition formula for P and the fact that P and P prime express any elliptic function of U in this way, we can deduce that any elliptic function has an addition formula. Which might be very complicated, but still there exists some non-trivial relation between FU, FU1, FU2, and F of U1 plus U2. About such tema, I don't think we have enough time. So, any questions so far?
Yes, I have a question. Is there a similar proof of the addition formula for the Jacobi's function?
Probably yes. Yeah, and yeah, many years ago when I talked about elliptic function in Japan, one of the students proved their addition formula in the same way, but yeah, I don't remember the details. But anyway, there exists such a proof. We shall prove, actually we shall define Jacobi's functions differently by using theta functions. So our proof of the addition formula for the Sn function, for example, will be different. But anyway, yeah, there is such a proof.
Okay, thank you.
Sure. Okay, so yeah, just a moment. I want. Send you something. Yeah, this is a homework program. And this is today's file. And okay. So you see, this is today's exercise, and I wrote that there will be almost 15 programs, and actually I put 18 up to here. So let's consider that up to this part is the essential part, and the rest is bonus. Well, that means not very serious thing. We normalize the points by the points up to the program number 15. Anyway, yeah, this is the end of the problems. Probably I don't have time to check your answers if I would give you problems next week or next week. So any other questions?